Hello, welcome to Lab 1 Charged Tapes in Physics 2212. The purpose of this experiment is to observe the interaction of two pieces of charged tapes to calculate the excess charge on the tape compared to neutral. The materials we need for this are three 8-inch pieces of Scotch tape, a ruler, and two objects of about the same height for support. We also need access to ClosedScript Python for the computational model. The results we got were a charge on tape of 8.86 times 10 to the negative 9 coulombs, and this is equivalent to 5.5 times 10 to the 10 electrons. The fundamental principles we need here are gravitational force, which is the attractive force between two objects with mass, Newton's second law, which is that the net force on a system is equal to the change in momentum. Specifically, when change in momentum is zero, the net force is zero. We also need Coulomb's law, which is used to calculate the attraction or repulsion of two charged objects. So the initial conditions here are the length of the tape and the width of the tape, which we then use to calculate the area and the mass. We also need to calculate how much surface area of atoms there are. Another thing here is once the tape is charged, you test if it's positive or negative by rubbing a plastic pen in your hair, and then because that pen is negative and it attracted the tape, we know it's positive. And here we can see video of it interacting with my hand, which should be neutral. So here's the observed model we use. So as you can see, this tape is suspended between two cans, and then I'd hold up the other piece of tape and measure when it's at equilibrium, as in it's not pushing up any higher or coming down from gravity. So the measurement I got for that is 20 centimeters or 0.02 meters. The calculations while the tape was at equilibrium, meaning net force is zero, is that the force of gravity is equal to the mass times the gravitational constant, as you can see there, which can then be summarized by this free body diagram to be equal and opposite to the electric force acting upon it. We then can use the formula for electric charge discussed earlier to find the charge of the piece of tape. We then divide this by the charge of a single electron to determine the equivalent amount of electrons that have been on the tape. So here's the code I used. It works through that same process of calculations, but then outputs a free body diagram as well as calculations. So you can change these constants and measured variables and get this image. In all of the inputs, this should be at equilibrium, where the electric force is acting up on the top tape and down is the gravity acting upon it. As you can see here, the answers match my calculations. So what assumptions did we make and what errors did they contribute? We assume that only gravity and electrical magnetism act on the system, which is the top tape. This doesn't account things like air resistance and drag that on such a lightweight piece of tape would probably make an impact. We also assume that the tape is just a point charge with uniform charge distribution, when really different parts of the tape would be higher in charge or lower in charge, and the geometry of that is just too complex for us to accurately calculate, so we make this assumption. This causes the error of the equilibrium point is probably inaccurate, as well as like which part of the tape is this equilibrium point acting for. So if we could find more complex geometries, we'd find more accurate charge. Also, as the tape was just sitting around, it was losing charge to the surroundings. As negative charged objects, the electrons would be attracted to the tape, which would reduce the magnitude of its charge. So what if electrons had positive charge? If the electrons had positive charge and the protons had negative charge, the two tapes would be negative in charge, but would still repel each other and allow us to perform the same calculations. The weight might be slightly different, but that'd be so marginal, and we're not that exact anyway, so it doesn't matter. And then why do we need to minimize contact with the tape? The longer it interacts with the surroundings, the more its charge is neutralized, and eventually we won't even be able to find any equilibrium.